Hi, I'm Nishida from the University of Chicago. Today I'd like to present our work, HandMorph, passive exoskeleton that miniaturizes grasp. This work was done with Soichiro Matsuda, Hiroshi Matsui, Shan-Yuan Teng, ziwei, Kenji Suzuki, and Pedro Lopes. I have been interested in how we can understand the embodied experience of a smaller person, such as a smaller hand in this case, and apply it for supporting people who need to understand this embodied knowledge, such as designing products for smaller persons. To this end, we developed a passive hand exoskeleton that miniaturizes a user's hand into that of a smaller person. Our exoskeleton allows congruent and real-time haptic feedback using passive mechanisms. These allow product designers to evaluate the usability of products with their own hands. Also, interior designers can improve the accessibility of classrooms where most of occupants might have a shorter reach. It consists of a globe, link mechanism, and smaller rubber fingers. We designed forward linkages with pin slots that miniaturize grasping motion. We also designed some linkage that miniaturizes grasping motion while preserving unconstrained movements. In combination, these features recreate a smaller grasp. Furthermore, this wire restricts the user's arm reach. This recreates a shorter reach. Let me explain how HandMorph is different. There have been several attempts to reproduce the sense of being a smaller person, such as transferring one's ownership to a small doll by using the technique of rubber hand illusion, or having a smaller avatar in a virtual environment. These change users' size and distance perception and even attitude, but only in VR. Recently, a wearable device that lowers the height of visual perspective in real time has proposed for assisting education and design process. In our case, we focused on recreating the experience of having a smaller hand in the real world while preserving interaction capability. To explore the effect of using HandMorph on our perception, we conducted a preliminary size perception study. In this study, participants interact with 5 different diameters of balls, then report their perceived size while blindfolded. The results suggested that objects were perceived to be larger than they were when wearing HandMorph. Smart sensory feedback and reduced action ability could affect the perception. Next and more importantly, we tested HandMorph in a setup closer to its intended usage, where a designer is working on a product to be used by children. In this study, we observed the experience of using HandMorph for evaluating and improving ergonomics of the toy trumpet. Participants were asked to improve the design of the toy trumpet for children. We provided a hand dimension sheet and HandMorph. Participants were allowed to use both tools as often as they wanted. We observed that some participants used HandMorph not only for testing ergonomics, but even to model the clay directly. Participants stated that smart sensory feedback helped them to understand the usability of their design. A post-questionnaire revealed that the confidence in their final design and the understanding of the usability has improved by the use of HandMorph. Exhibition visitors were able to quickly learn how to use and to interact through the exoskeleton thanks to its passive mechanism form factor. Taking these results together, we believe that HandMorph affords a wider range of applications that promotes more embodied design process. This also raises an open question, which is that changing bodies also change our own perspective. I have been tackling this question through sharing kinesthetic perspective of a patient by sharing muscle activities, shifting visual perspective to lower position for nursing school teachers, and now morphing haptic perspective into smaller hands. Our future works include miniaturizing other parts of limbs and investigating the changes in perception, action, and interaction. Thanks for watching.